This video segment continues to examine the direct effects of rising atmospheric carbon dioxide concentrations on plants. It focuses on the influence of carbon dioxide enrichment on nutrients, especially nitrogen. Its major points are: number one, nitrogen is the mineral element that organisms require in greatest amounts. Number two, most organisms cannot directly access the huge reservoir of inert nitrogen in Earth's atmosphere. Number three, most plants acquire their mineral nitrogen through root absorption of inorganic nitrogen ions from the soil solution. Exposure to elevated carbon dioxide concentrations initially stimulates carbon fixation and growth in most plants, but after days or weeks or months of exposure, these processes slow down. This decline is known as carbon dioxide acclimation. We have discovered a straightforward explanation for carbon dioxide acclimation. It involves the interactions between photosynthesis and plant nitrogen metabolism. Most of you will require some background information before you can appreciate this. Sugar and spice and everything nice. That's what boys and girls are made of. Boys and girls obtain their sugar and spice from plants, but where do plants obtain their materials? The most plentiful elements, oxygen, carbon, and hydrogen, derive from water or atmospheric gases. Plants mine all the remaining elements from the soil. These mineral elements constitute the third corner of the plant resource triangle. The other two corners of the resource triangle are energy and water. Nitrogen is the mineral element that organisms require in greatest amounts. It constitutes a vital part of many organic compounds, including proteins such as ribosco, and nucleic acids such as DNA. Application of nitrogen fertilizers stimulate nearly all agricultural and natural ecosystems. Consequently, nitrogen availability is considered to be a major factor that limits plant productivity. You may now be able to answer the riddle: what is scarce, although it is literally surrounding us? Earth's atmosphere contains vast quantities of molecular nitrogen, about 78% by volume. Most organisms, however, cannot directly access this huge reservoir because of the exceptionally stable triple bond between the two nitrogen atoms that renders it an inert or noble gas. Breaking this triple bond to generate more reactive forms such as ammonia or nitrate requires enormous input of energy. Chemical reactions of such energetic proportions do occur during the process known as nitrogen fixation. Nitrogen fixation occurs both industrially and naturally. In industrial nitrogen fixation, molecular nitrogen and hydrogen, when subjected to elevated temperatures, 400 to 650 degrees Celsius, and high pressures, 200 to 400 atmospheres, and a metal catalyst, usually iron, form ammonium. N2 plus 3 hydrogens plus energy yields 2NH3, or ammonia. This is called the Haber-Bosch process, which was developed during World War I when Germany required high-energy nitrogen compounds to produce gunpowder and other explosives, but the British Navy cut Germany off from its supplies of saltpeter, sodium nitrate, mined in Chile. Nowadays, most industrial nitrogen fixation is directed toward agricultural fertilizer production. We have beaten our swords into plowshares. Industrial fixation exceeds 88 billion kilograms of nitrogen per year. Agriculture in the United States of America consumes about 14% of the world's total, but its fertilizer use has remained relatively constant over the last decade. Fertilizer costs, because of the high energy demands of industrial nitrogen fixation, are strongly correlated with power costs.